manifold is 4n-dimensional. We said it's quatonic Kähler. Which I'm going to abbreviate into QK, quatonic Kähler. If polynomial group at a point P is contained in SPn SP1, where I identified TPM with Hn in some fashion, and SPn SP1 acts on Hn in the usual V, where that V goes to AV Q inverse. So this was one definition of quatonic Kähler, and then remember also, if I have stronger than that, if Hall P is contained in SPn, then it was called hyperkähler. Generally abbreviated HK. So quatonic Kähler and hyperkähler. Then the theorem I wanted to first prove was give a geometric definition of quatonic Kähler. So we let E be the endomorphisms of Tm. This is a vector bundle over M. At each point, the endomorphisms of the tangent space. And then we say quatonic Kähler is equivalent to saying that we have a parallel subbundle F containing E should be three-dimensional, such that for all P in M there exists a basis J1, J2, J3 of F at the point P, such that the Ji's are orthogonal complex structures which intercommute. So this is a more geometric way of defining quatonic Kähler, and in this fashion one can prove things easier. And for example, shows that something's quatonic Kähler, you do this in terms of this kind of structure, these parallel subbundles. Of course, here, I mean, maybe it's clear what I mean by parallel subbundle, right? So if you have gamma goes from P to Q, then parallel translation goes from F, say Fp to Fq by taking an endomorphism A into A composed with P gamma inverse composed with P gamma. So parallel translation conjugates like this. So this now is an endomorphism from Q to Q, and you require that lies in Fq. Equivalently, there's another way to say that. If A is a section of F, so in other words, for each point P, AP lies in Fp, and X is a vector field on M, then I require that the cone derivative of nabla XA at each point P is an element of Fp. So cone derivative sections stay in the bundle. It doesn't say there's a basis of sections which are parallel. It doesn't say that. Particularly this bundle F here, in general, doesn't have any sections. Maybe the simplest example, which I mentioned last time already, was HPN, which is SPN n plus 1 divided by SPN SP1. It's a symmetric space, so the Horner group is all of SPN SP1. So the most extreme case of being quatonic Kähler, and HPN is not scalar, certainly, because H2 is 0. Right? So that means that these complex structures here can't be parallel. You can't have any parallel complex structures, so no parallel section of the bundle. That's impossible. Or the bundle itself is parallel, but there's no parallel sections. So that's the difference. And even worse than that, and HPN has no even almost integral, no almost complex structures. So that means there's no section whatsoever, parallel or not, of this bundle F, this particular example. Not sure how one proves that it has no complex structures. Okay, so that's a word of caution in this kind of definition here. Unlike for hyperkähler, right? For hyperkähler we had 3 parallel complex structures. So this is a special case where the bundle F has a parallel basis. That's hyperkähler. Okay, in the proof.
Is it easy to prove that this guy doesn't have any almost complex structure?
No, I don't think so.
Some kind of structure in characteristic classes.
Yes, so how would I do that? Probably by the frame bundle. So if you have a manifold M, you can always look at the frames over M. See, I choose a Riemannian matrix, so I can make it into an ON principal bundles. These are the orthonormal frames. And what's the complex structure? The complex structure is a reduction to UN. So this is even dimensional. So this bundle here is classified by a map into the classifying space of O2n. With a reduction to UN, that means I have a subbundle. So inside the frame bundle, it's classified by a map into the classifying space of UN. And so to have a complex structure means the following. Can I factor the classifying map of my whole bundle, which goes into the orthogonal group, because I can also assume it's orientable since the complex structure has an orientation on it. Can I factor that through map into the unitary group? Right, UN lies in SO2n. I get an induced map into the classifying spaces, and that's an orientation or Riemannian metric, oriented Riemannian metric. That's a complex structure. So can I factor it like this? And there are obstructions to these kind of questions. And my guess is that's how you prove in this case. Okay. Let's see. That's probably how you do it. Okay, yeah, this is how you do it. But you know a little bit about characteristic classes, not very much. The Pontryagin classes, right? So PI in H4I of the vector bundle. And then if I have a complex vector bundle, there are Chern classes CI, which lie in H2I. These are invariants, characteristic classes of these kind of bundles. For relationship between these classes and these classes is, for example, that P1 is C1 squared. First Pontryagin class must be C1 squared. Because for HPN, this lies in dimension 2, there's nothing in dimension 2. This has to vanish. That means the first Pontryagin class would have to vanish. But you compute that for HPN and show it's non-zero. So that would be how I impose it. And this kind of computation is done in Milner's book on characteristic classes, for example. It discusses all these examples. Certainly a book I can recommend reading sometime. It's Milner's book on characteristic classes is a beautiful book. It's very well written. All his books are beautiful. Has anyone looked at that book or read it? No? Milner's book on Morse theory? What? Milner's book on Morse theory, have you read that? Another beautiful book. Okay, we got distracted. For the proof, I need the following lemma, which is useful in its own right, was later on. So it's just a fact about a vector space. We have an embedding of SPn, SP1 inside SO4n by this action here, right? This is how it acts on R4n. After I choose an identification. And now I claim that SPn, SP1 is a normalizer of the SP1 factor. Remember, this here is a dot, right, which meant that it's really a product divided by a diagonal Z2, but nevertheless it contains as a subgroup SP1. I don't have to divide by the Z2 because this sits in here diagonally. So this is a subgroup of this group, therefore a subgroup of SO4, and this normally of this in SO4n. So that's what I want to claim. Okay, this requires a little argument. Not quite obvious. One inclusion is clear. Let's give these a name. Let's call K equals SPn SP1. And let's call N the normalizer of SP1. And let's write like this. Okay. Then certainly K is contained in the normalizer. It's just a local product, so certainly normalizes SP1, so you have to show the other direction. So I want to show N is the normalizer is contained in SPn dot SP1. So let's take something in the normalizer. So let's take an element A in SO4n, which normalizes the SP1. So what does that mean? It means that if I take an element Q in SP1, remember it acts via right multiplication, so it must normalize this. That means that this must be again a right multiplication, but by some possibly different element. It's called a Q prime. And this defines for me a homomorphism. First a map from Q to Q prime. Let's call it alpha. And because this is given by conjugation here, it's not hard to see that alpha is a homomorphism. Now I claim, let me separate this a little bit. I claim that out SP1s, the automorphisms of SP1, are the same thing as int SP1. So in other words, given by conjugation. So out is equal to int for this Lie group. I'm doing this on the Lie group level, so on the Lie group level, int would be conjugation. Okay. If I know this, so from the claim, I claim, so this does what I want, because this would then mean that here's my homomorphism. Of course, it's not hard to show that this is also an isomorphism. So this homomorphism actually lies in out SP1. So it's given by conjugation. So alpha is conjugation by some element Q0 in SP1. So it means that, means what? It means that if I compose A with CQ0 inverse, so in other words, I undo whatever A does on the SP1 factor by this conjugation, this acts trivially. On SP1, I commute with SP1. What does it mean to commute with SP1? How does SP1 act? It acts by right multiplication. That means that this map must be quaternion linear. Okay, so this says that hence it's H linear, which implies it's an element in SPN. These are precisely the H linear maps. Left multiplication by element SPN was are precisely the maps which are linear, and the right multiplication by quaternions. So now you're done. So A composed with C Q naught inverse is element B, which lies in SPN. So A is C Q naught composed with B, so it lies in SPN, SP1. Okay, so this claim here would do it for us. So let's see why this is true. There are no outer automorphisms of this group. That's what the claim is. Well, so let's take an outer automorphism, or some automorphism. Since SP1 is simply connected, this is determined by the derivative for A, which is an automorphism of the Lie algebra. With respect to a bi-invariant metric on this Lie group, it's a compact Lie group, so it has a bi-invariant metric where dA is an isometry. So automorphisms, for example, let's say the killing form. Take the killing form, right? Every automorphism preserves a killing form. Maybe that's better. Which is negative definite on this SP1. I could take minus the killing form, make it positive definite. Anyway, automorphisms preserve it, so the isomorphisms, isometries in this killing form. So dA is actually an element of the orthogon group, but since the group is connected, also the special orthogon group of this Lie algebra. Because this Lie algebra is three-dimensional, SP1 is three-dimensional, so dA lies in SO3. So I get a map from dA lies in SO3. So on the other hand, I can now say I also have a map given by conjugation, the automorphisms. They also define a map into SO3 by taking Q into by conjugation. So at Q. That's also homomorphism. But of course, notice it's a homomorphism. They're both three-dimensional. Right? What's the kernel? The kernel is the center. That's plus or minus identity. So this must be onto. Since both are three-dimensional. So it means everything in SO of the Lie algebra is actually inner. Right? So that means that this dA, which lies in SO of the Lie algebra, must be inner. So dA is equal to at Q, which implies that A is conjugation by Q. So that's the proof. It was actually true that also at SO odd, for SO odd, every automorphism is inner, which is a little more difficult to prove. I don't think we ever did that. But for SO3, it's elementary, because for dimensional reasons. For SON, if you go into SO of the Lie algebra, this thing has much bigger dimensions than the group itself, so this is not going to work for SO odd. But for SO3, it's very easy. So that proves a claim. Every automorphism is inner, and that finishes the argument of this lemma. So SP1 is a normalizer. So now we want to use that to prove this equivalence of being quaternion K. So there are two directions. So first, let's prove this direction. So if all contained in SPn SP1, I have to construct this kind of subbundle with this kind of basis. So because you're picking a point P, so there's some base point where I do the holonomy. Right? This notation means I've already identified TPM with HN. And then it acts in the standard form on HN. And I can let's call this point P naught, right? This is my fixed point. Define FP naught as, so my three-dimensional bundle, I'm going to define by ref translation by Q, where Q is an image. Right, that's a three-dimensional space sitting inside the endomorphisms of TP naught M. And this has a basis. Right multiplication by I, right multiplication by J, right multiplication by K. And these are anti-commuting orthogonal complex structures, just directly required at that point. Right, so that's this condition that they have J1, J2, J3. That's at the point P naught, and now I'll push it around using our holonomy principle. So we'll now define f at Q as P gamma composed with Fp composed with P gamma inverse in the sense that we discussed before, right? So push those gamma is a point from P naught to my other point Q, push it around with parallel translation, and since all at P naught preserves f at P naught, right? That's what this is here. Here's holonaturalizing here. These are right translations. SPn acts trivially by right translation. Right translations normalize it. It doesn't act trivially, but it normalizes it. Right? And so hints well defined. So it's our holonomy principle. And parallel by definition. And that's it. So I have a parallel subbundle of endomorphisms, and I have a natural basis at the point P naught. And of course, if I parallel translate that basis, I get another thing like this at my other point. And so is a required basis. These are symmetries, since P gamma is and Ri is, they're complex structures, and they anti-commute, easily crank it out. So that's one direction.
Why is this only local?
It's not local, it's global.
It's global. But the definition, why is it only?
Or the complex, these complex structures, you mean? Or what? Because when I push them around with my holonomy, say conjugate something in SP and SP1, then this SP1 will change Ri to some R something else. That means if I go to a different point with this group here, if that element, if that holonomy thing contains something in SP1, it's going to change that complex structure to a different one. But it's going to change it into a complex structure which is some linear combination of these three. So it still lies in the three-dimensional bundle. But it will change the complex structure.
Wouldn't it look like a complex structure, an almost complex structure?
If you think of the complex version, then the SP1 would be the analog of U1. Like then it lies in UN, just SUN times U1. U1 is a billion, so it doesn't matter. Right? So if I have something in here which is a complex structure, then it's well defined because U1 is a billion, and then it's preserved. But SPN is not a billion, so if it really has something in here and is not contained in SPN, if it's contained in SPN, you're fine. Right? Then it just preserves these, and each one gives me a complex structure on the whole manifold, a parallel one. So if it's contained in here, that was hypercoelent, then you're okay. If there's some component here, it'll change this from point to point. Okay.
For example, the parallel transport along gamma of right multiplication by I, but the conjugation by the parallel transport, will have square minus identity.
Yes? It's not well defined, right? So what would be the problem? Here I take my point P naught, I take a closed path P gamma, and then P gamma composed with Ri composed with P gamma inverse is equal to R times some Q prime, some different right multiplication. Right? That means if I want to define my complex structure at this point here, if I go this way or this way, I'll get different complex structures here. Because if I go around the closed path, it's going to change the element with which I have to right translate. So I can't, it's not well defined. So I can only apply the Holonomy principle to the bundle, but not to each individual element. Okay? That's one direction. So the other direction, let's say given such a bundle F, all these properties over there. I want to show that the holonomic group, so now I need to show a hol in SPN, SP1. So fix a point P naught. And choose some representative J1, J2, J3 of F at P naught. This helps me identify TP naught M with HN. And letting this be multiplication by I, by J, by K. That gives me multiplication. And SP1 X by right multiplication. So I can view F at P naught as the set of right translations. That's my bundle that's spanned by these three right multiplications. And Hol preserves F, right? Since F is parallel, particular preserves F, and hence normalizes the right action by SP1 on HN. And now by the lemma, this implies that Hol is contained in SPN, SP1. Because this lemma says that the full normalizer, or this right translations here, full normal of the right translations here is SPN, SP1, so it's contained in there. So that's it. Let's come out. This whole thing is based on this simple fact about Lie groups. Okay, so that's a nice characterization of quadratic Kähler. Before I go to symmetric space, which are quadratic Kähler, which are the basic examples of compact ones, let me explain what a twistor space is. So studying these quadratic Kähler manifolds, although a priori they have nothing to do with complex geometry, there's no complex structure, it's not a complex manifold in general, but you can nevertheless use complex geometry by defining what's called the twistor space. It's an important object, and I think it's really neat the way it's defined. So or the quaternion Kähler manifold, or hyperkähler. That's against the hyperkähler case, since that's an example of quaternion Kähler. So what's the twistor space? Let's call it Z. Z is defined as the sphere bundle of F. So let's use it, let's normalize in the following fashion. So set of all, say at the point P, this is again a vector bundle, would be all endomorphisms in FP, such that the inner product of AP with itself, so unit sphere bundle would be 1. Here the convenient normalization is 2n. We'll see in a minute why that's convenient. That's not so important. It's the same space when I set it equal to 1, right? There's a natural map from one to the other. But just for convenience, I'm going to define it like this. Because on the endomorphism, I have my usual inner product, right? AB is equal to trace of AB transpose. This is an inner product on the endomorphisms of my vector space. So that's the inner product I'm using with respect to this. Now notice that if J is my orthogonal complex structure, in F, then I claim it lies in Z. So J is an element in Z. What's the inner product? J comma J. It's so what is J? J is orthogonal. It's a complex structure. And that also means it's skew-symmetric. So it's skew-symmetric, so transpose minus it. So it's trace minus trace J squared. J is skew-symmetric. It has the usual normal form, A minus A0, block form, and so on. It's also J squared minus identity. Since the square is minus A squared, this must be 1. That's some orthonormal basis where J has this normal form, and the square is then a -1 along the diagonal. Maybe I should do 4. Yes, 4 and square is -1 all along the diagonal. My minimum holds 4 n dimensions, so let's make it 4 n. Just so that my orthogonal complex structures are elements of Z. Notice also the following, that if J1, J2, J3 is my basis of F at that point P, which is required in the definition, if I then take a linear combination where I assume the sum of I squared is equal to 1, this implies that J is also a orthogonal complex structure. And in fact lies in S of F, in the twistor space. So any linear combination of my basis elements, as long as the combination has summation A squared equal to 1, also lies in S of S. So, for example, what? It's certainly skew-symmetric, right? Is this clearly satisfied? If I square it, I also need the anti-commute. That's part of the definition. So that's easy to show that if you square it, G squared is minus identity. I think for this I need this normalization. So if you wanted the fiber over this SFP, it can also be regarded as a set of orthogonal complex structures in FP.
That is at least clear to me if I have a base of complex structures.
What?
If I have a base of complex structures,
Which anti-commute?
which anti-commute for F, that is clear. So just from like they always have a base of complex structures.
That's part of the definition. So I'm given F. That means there's some basis, not canonical. There's some basis of compact structures, orthogonal compact structures with intercommute. Okay. Then I get a whole two-sphere, if you want to, of orthogonal compact structures, like this. Okay. And that's what the fiber looks like. Let's look at a set of all orthogonal compact structures in this three-dimensional parallel subbundle. Okay. So that's called the twistor space. And actually, and this becomes a complex manifold in a very natural way. It's a really neat definition. First, notice that there's a natural projection from the twistor space into M, which sends my endomorphism or my complex structure into the foot point. And what's pi inverse of some foot point P? So that's the fiber here, that's a set of orthogonal complex structures if you want to. And this was this object, so another way of writing was summation aij for some basis. Summation a squared is equal to 1. So it's a two-sphere. And S2 is CP1. So it certainly has a natural complex structure. Right? So in this fiber bundle, I have a fiber bundle. And at least the fiber has a natural complex structure. The base doesn't. Right? But I want to put one in the total space. So how does one do that? I want to put a metric on Z in order. So this on the fiber I have a complex structure. So I have my fiber bundle, right? So think of it like this. Here's my base. Here's my fiber bundle. My fibers are CP1s. On this space here, there's a natural complex structure. I have to define one transversal to that. Okay. Transversal to that, I can project onto the base, and projection will be an isomorphism. But of course, there's a priori no natural choice of the transversal. And that's something I want to solve by using some geometry. So we have a metric on M. We have a connection on M. It's a metric connection, it's Levitz Vita. Right? This induces a connection, a metric, and a connection on the endomorphism bundle. The metric I wrote down up there. Connection is just the usual connection, differential endomorphism, and hints on F. In fact, this is even a parallel subbundle, right? So co-derivative of a section is in it. So in general, one might have to project into a subbundle. Here, I don't have to do that. Right? There's a very natural metric on it, a very natural connection, and the connection is metric. I.e. preserves parallel translation. Sorry, yes, preserves. Parallel translation has symmetries. In other words. So that I have always, right, on the whole tensor algebra, I have a natural induced connection. Once I have that, there's a canonical way to define the complement. And that's called a horizontal space. So I define what I want to call the horizontal space at a point in Z. What's a point in Z? It's an orthogonal complex structure. Right, that was one way to view it. A set of all J's which look like this. This is an orthogonal complex structure. So take a point in Z that looks like this, an orthogonal complex structure. I want to define a vector space at this point. So that's my point here. So that defines a complex structure on the base, right? Because that's this J here exists is a complex structure on the tangent space at the point P by definition. There's no canonical choice of a complex structure, but if I look at the bundle of all possible complex structures, if I pick a point, there is a complex structure on the base. For a different point in the fiber, the different complex structure on the base. But first I have to, and then I'm going to pull back this complex structure from here to this complementary space. Let me first define it. If you've seen, say, this kind of discussion which Duchamp does at some point of how to define the metric on the tangent bundle, the connection of the tangent bundle. We define a vertical space and horizontal space. I can copy this and define this here as ddt of j gamma t at t equals 0, where j gamma t is an element in this twistor space. So it's a complex structure at the point gamma t, right? An orthogonal complex structure in the space at the point gamma t. Gamma at 0 is my point. This here is in z at p. Starts at p, and gamma prime at 0 is some vector v in TPM. And in addition, J is parallel. So in other words, right, take your point. So in this picture here, take your point P, go in some direction, all the various direction V in the base. Then, and my initial J is well defined there. Take that J, go along that path, and parallel translate. It stays in F because F is invariant in the parallel translation. So I get a parallel section of an orthogonal complex structure, but only along this path. But I can't do it in the neighborhood. There are obstructions to that. Along a path, there's none. Just take something, parallel translate along the path. Then I have something locally defined along the path. I take this parallel section and I differentiate, and I get a vector. This now lies in Z. The derivative lies in the tangent space of Z. So this here is contained in the tangent space of J of the manifold Z. And notice that I have a projection, Hj to the tangent space of P at M. In fact, it's just phi star, which takes this d dt at t equals 0 of j gamma t into V. Right, what's the projection do? It looks at the foot point. The foot point of my path is gamma t. Its derivative is just V. And this is an isomorphism. Okay. And that's complementary to this vector space here, where I don't change the foot point at all and only stay in the fiber. So that's called the vertical space. So vertical space at J is space tangent to the fiber of this bundle. And now I simply say, well, make this orthogonal to the horizontal space. Pull back the metric on Hj. So such that pi star is an isometry. This is an isomorphism. I have a metric here. I pull it back to the horizontal space. I make these two orthogonal, and on the fiber, on CP1, I have a natural metric. So, regard S2, the round symmetric, for example, right? So the fiber has a natural metric a priori, because it's the CP1. So I define, by a parallel translation in this fashion, I define some kind of complement. I make them orthogonal. That's my definition. Right? Here I have a metric on S2. Here I have a metric as a pullback from here. Okay. So that's how you put metrics on the total space of any vector bundle, in fact. Right? So take a vector bundle, take a metric, take a connection, and then look at sections which are parallel, differentiate. You get something tangent to the total space. That's complementary to your fiber. And so you have a natural decomposition of the tangent of the total space in something tangent to the fiber and something complementary given by in terms of connection, like parallel translation. And then you can use that to put a metric on the total space. So a very general kind of setup. And now I can define my complex structure. So now I'm done, I claim. So I define, what I call that, or using J bar. That's an almost complex structure. On Z. So my tangent space of Z at a point is the vertical space at G. The orthogonal diapason with the horizontal space at J. And on the vertical space, I choose a complex structure on CP1. And on the horizontal space, I pull back J on TPM by the projection. So this point J defines me something down here. So I pull that back, and that defines something on the horizontal space. And of course, so the complex structure preserves this, takes this to this. Here just take a small CP1 and take this to this, and here it's the definition of the foot point. It's really neat. And then the big theorem is the following. If M is quadratic scalar with positive Ricci curvature, then Z is scalar Einstein. And pi is holomorphic. So that's the connection to complex geometry. So now I have a nice complex manifold upstairs. These are in fact very special. You can say lots of things about this complex manifold here. And one can do complex geometry upstairs and try to deduce something about the quadratic scalar manifold downstairs.
We already have a complex structure without the Ricci condition.
Pardon?
Without the Ricci condition, we do have the integrability of that complex structure.
No, not yet. I have to prove it's scalar Einstein. Then it's integral. Just this is Ricci curvature to the base, right? So in this twistor space, the base has positive Ricci curvature. That doesn't imply anything as far as complex structure is concerned. The base doesn't have one, right? The total space doesn't have positive Ricci curvature, not necessarily. Well, actually it does. But anyway, this is not going to help you. You have to prove it's scalar, and then it's integrable. So here now, I just have to find an almost complex structure, and part of the problem is going to be I have to prove it's integral, or that it's parallel, if you want to, right? So it's scalar Einstein. Okay. So I wanted to explain the twistor space because that's an important part of this kind of story in general. Okay. This has been used also in similar contexts. Kind of this idea that if you look at in some fashion, a space of almost complex structures with a nice fiber, then you can put a complex structure on it tautologically, because a foot point is a complex structure. That's the basic idea. That's kind of neat. Okay. I'm not going to use it again. So now we'll do symmetric spaces, which are quadratic scalar, because these are the basic examples.
It's not almost the same that defining the tautological bundle of CPN?
No. You mean like the canonical line bundle, or what? Yeah. And the canonical line bundle even also has a complex structure. It's a complex manifold, but in a more direct fashion. There you don't have to play this kind of role. Okay. There on the base you also have a complex structure, right? If the base has a complex structure, then it's much easier. Here you don't. The base doesn't have a complex structure. That makes it different. Not hard. Okay. Symmetric space, let's define as follows. So let's look at the M is a symmetric space. It's called quaternion symmetric. If it's symmetric, if it's quaternion scalar plus symmetric. And the relation between the two structures is that n SP star F is equal to F for all symmetries SP. So for all points P, I have an isometry SP defined on a whole manifold. I can pull back my endomorphism bundle with that isometry, and I'm supposed to get the same bundle at different points. So that's my compatibility. And I can call it quaternion symmetric. So by definition, they are quaternion scalar. We can simplify the definition a little bit in a minute. Maybe, forget if I mentioned this, I probably forgot. When you look at this whole story of being quaternion scalar, you should assume that n is bigger than 1. So we had SP and SP1 for 4 n-dimensional manifold. N equal to 1 I claim is silly. It doesn't mean anything. Because then, so this was contained in SO4n, right? So for n equal to 1, I have SP1 dot SP1 contained in SO4n, in the SO4, but they're equal. So SP1 dot SP1 divided by the diagonal Z2, it's precisely SO4. So in dimension 4, quaternion scalar doesn't mean anything. It just means an orientation and a metric. Right? So you always want to assume n bigger than 1 whenever you talk about quaternion scalar manifolds. Okay. There is an analogous concept in dimension 4 called self-dual Einstein, but that has to be defined differently. We can't define it as a holonomy. Okay, let's prove something about the symmetric spaces. What should I do first? Let's maybe first give a pointwise definition, just like we did for a Hermitian symmetric space. So let G, K be a symmetric pair. And G is equal to K plus P, my Cartan decomposition. P identifies usually the tangent space at my foot point. Then this is quaternion symmetric. Such a symmetric pair is quaternion symmetric if and only if there exists J1, J2, J3 from P to P, again, anti-commuting complex structures. Orthogonal. Such that at K preserves the span of those three. If you want to, that's my definition of my bundle at the point P naught at my foot point. So I claim I only have to study this condition at a single point. So then I make a choice of some three orthogonal anti-commuting complex structures, because that choice, I mean, this is not a strong condition as long as this is 4n dimensional. I always have these identified with hn, look at the right multiplication. This by itself says nothing, essentially. But then this says that it must be compatible with the isotropy representation. At K must preserve the subspace. Kind of analogous to what we did with Hermitian symmetric spaces. There we said, well, P had to be a complex structure, and at K had to commute with it. Right? Then it was an integral complex structure, was Kähler-Einstein and everything. Right? This is our pointwise condition for Hermitian symmetric. Here it's this, the analog is that the span of these three things is preserved by at k. And the proof is the same, so it's based on the fact that the holonomy is contained in K for a symmetric pair. So something we proved for symmetric spaces. Holonomy gives a subgroup of K. If it's irreducible, not a Euclidean pair, it's equal to K, but here just a subgroup of K. So it means that Hol preserves this f at K, this now a Pell translate. Just like I did before, right? And just like we did in the proof for the theorem over there. That's it. Right? So very nice, simple pointwise description of when a symmetric pair is quaternion symmetric. I want to characterize that in a simple fashion. I can recognize right away that a symmetric pair is quaternion symmetric. In a similar fashion, I mean, we had a similar characterization also for being Hermitian symmetric. There was simply that K has to be has to have at least a one-dimensional center. Right? It's Hermitian symmetric if and only if K was not semi-simple. That was our characterization. If it's irreducible, K just had a one-dimensional center, a circle. That gives me a complex structure. So I could see right away which symmetric space are Hermitian symmetric just by looking at K. When is K semi-simple, when not? That's the analogous characterization here. G comma K, let's assume it's symmetric, quaternion symmetric. Pair.
Is it clear that the symmetry preserves F?
That what?
That the symmetry is.
Okay, you're right. I do have to prove something. Thank you. I want to prove this. Forgot about that. So that's a little argument. Let's see what we have to do. Forgot about that. So we had a similar thing for Hermitian symmetric spaces. Right there we showed that symmetries preserve the complex structure. So there we defined that J on P, assume that at K commutes with J. Then we moved around with pair translation into a complex structure on the manifold. And then we proved that the symmetries preserve the complex structure. And I just want to copy that proof. How did that proof go? So let me just, I think, indicate it. How is f at q defined? F at q is defined as p gamma compute composed with f at, what do we call this point? Foot point p naught. And now I'll pull that back with SPF star. So I claim if you copy that proof, there was a little trick in there to see that the complex structure is preserved. But if you just copy the identical same proof, you get that these are not necessarily preserved, because at K possibly permutes them in some fashion, right? But at least the symmetry that does the same thing. It at most permutes them and preserves F. So
Should it reverse the Chodestic?
symmetry is reverse suggestive, but of course here I mean that so SP goes from M to M, right? And I take so what does it mean if I take A as an anamorphism at some point R, right? Then DSP at the point R, so you have to do it at every point, right? Lies in F at the point SP of R. At the point P, it's clear because at the point P is minus identity. So then certainly when you conjugate, you preserve it. The foot points, the point where I flip is not the issue. I have to also put the other points.
What I meant was, for example, the pullback under SP of FQ, the one we're writing there, should be the parallel transform under the inverse of gamma.
But I have to apply the symmetry. This by itself is not parallel transport. Composition of two of them, the transvections were parallel transferred, but the symmetry itself not necessarily. So these linear maps here were not parallel translation. So there's a little argument here involved, but it's the same as for Hermitian symmetry. So let me skip that. So here I want to characterize a symmetric pair. Two claims. A, if the Ricci curvature is identically 0, then this implies that G mod K, my symmetric pair, is isomorphic to Hn. So Hn is a quadratic symmetric space in a very trivial fashion. That's always something we want to ignore. And in fact, if it's not identically 0, so if the manifold is not Hn, this implies lots of things. So maybe then the space is quadratic symmetric. If and only if the group K is K prime times SP1, where K prime is contained in SPn, and SP1 acts on P, which identifies the tangent space, as right multiplication by SP1. So it should contain my SP1. So quadratic K was a hologram is contained in SP and SP1. So the group should look like that, right? It should be a product of SPN with something else. That something else contained in SPN. So of course now K is contained in SPN, SP1 definition. But then I have the additional requirement that how SP1 acts on the tangent space should be like right multiplication. That's often called a Hopf action. So that's my analog of being Hermitian symmetric if and only if K is not semi-simple. K must split off from SP1, and that SP1 must act like the Hopf action on the tangent space. That's it. Let me maybe do some examples, some application of that. The first example we've seen already, right? So SPn plus 1, SPn, SP1 is a symmetric pair. Gives me HPn, so a certain case, all of SPn, SP1. The next examples are somewhat less obvious. The Grassmannian of two planes in Cn. Complex Grassmannian is quadratic Kähler. But only the two planes. So how do they describe the SUN? But SUN acts on this, and then I divide by S of UN U2, U2 UN. These are complex two planes. So the stabilizer preserves a two plane and it's a orthogonal complement. So that's my K here. This was a symmetric pair. That's my G, this is my K. And I claim K contains an S and SP1. Let's think of it as SU2 that sits inside U2, which sits inside S of U2, U2 UN. Or there's a terminal 1, so I only have to put something here and nothing over here. So SPN is a subgroup of this. So notice that this means that I can write S of U2 UN as dot SP1, where what is this something that has to be left? What could it be? I already took my SU2 out, that's my SP1. Here I have a two-dimensional center, a U1 and U1. I take the determinant 1, there's a one-dimensional center left. Here I have a UN, so I claim it just should be up to covers UN dot SP1. So maybe that's how I denote the dot. So it looks up to covers like UN dot SU2, and SU2 is SP1. So this first condition is satisfied. Right. Looks like this. But now I have this other condition that the way the SU2 acts must be like the Hopf action. So how do I do that? So I have to compute at K. This here, the film I just erased here said I should compute at K and see that at K preserves an excellent tangent space like that. So if I look at G, at the Lie algebra G, breaks up into block form. Here's my 2 by 2, here's my n by n. Stabilizer was a block here and a block here, right? And so that was my K. What was my P? The complement was something of the form in X here, nothing in H, and minus X transpose here, because it's Q-symmetric. So X had to be 2 by n. So I could then identify P with a set of such X's, which I can think of two vectors. Right? So my X has two rows given by two vectors. That means I can identify this here with Cn plus Cn, which I identify in the usual fashion with Hn. We're taking the two rows into V plus JW. How does the isotropic group act? So what is at K? Isotropic group is given by two matrices, U2 and UN. So I claim that at A comma B on X is simply AX B transpose. So that's a little computation conjugate to this, right? That's how you see what the action is. So that's the isotropy action. My group that I want to look at is SU2 inside there, so I want to set let A be an SU2 and B trivial. So that's why left multiplication on the matrix X, and this left multiplication lies in SU2. SU2 identified with SP1 as usual. And how was that? Well, if this is something of the form A plus JB, this became A B minus B bar A bar. So now I can write out how does this element act on this matrix X or translate it on Hn. And now you can check in this computation we've done before that SU2 acts by the Hopf action. So that additional check I have to make, just because the SU2 is a factor in here, that's not sufficient. You have to also see how it acts in the tangent space. So that's one space. What's another example? The real Grassmannian of 4 planes in Rn. It's also Catonic symmetric. So as a symmetric pair, rho is SON divided by SO4 SON. So oriented Grassmannian. SO4 SON. That's my K. Doesn't have immediately a factor of SU2 in there, but remember that I have a two-fold cover into SO4. Give my left and right translation. Okay. And the kernel was -1, -1. So it means that SP1, the image of SP1, is a subgroup of SO4. It's not a quotient, it's not SO3, it's a subgroup. Right? So that's my SP1 in K. So if you want, I can think of K here as SP1 dot SP1 dot SON. Because this SP1 dot SP1 I interpret as SP1 divided by diagonal Z2, and that's SO4. Okay. And now that's one containing there. The first condition is satisfied. I have this factor SP1 in here. Now I want to see how it acts on tangent space. And there I do a similar computation. So here I have 4 by 4 matrices, n by n matrices. P was then analogously x minus x bar x transpose. Here I forgot the bar, right? And again, A, B acts on there in the same fashion. Right? Just like before. So now A lies in SO4. I can think of this X as 4 row vectors. Right? So that's an element of our n plus our n plus our n plus our n, which is Hn, identified. Right? SO4 acts on this just by left multiplication with the matrix. Right? And if I think of SO4 as SP1, SP1, this acts by a left multiplication or right multiplication on R4. If I pick out one of these, or this one, doesn't matter, it acts by definition as right multiplication on R4, which is H. And in the same fashion on R4n plus Hn. So that's it. Right. Then there's a theorem. So I've given you all the examples which are quotients of classical Lie groups. That's it. So the theorem which says that quaternion symmetric, which are not equal to Hn, which is an interesting one, are in one-to-one correspondence with simple Lie groups G. Complex simple Lie groups G. So here's SPN, SUN, and SON. These are the compact simple Lie groups for the classical groups. So I gave you each quotient that is quaternion symmetric. Then for each exception Lie group, for each one of the 5 exception Lie groups, there's again a quotient which is quaternion symmetric, and that's the full list. Let me just write down what the correspondence is, and then maybe I finish. That's quaternion symmetric. So what you do is how to define K and G. So take my compact Lie group G, choose the maximum B and subalgebra inside G, look at the roots, look at the positive roots. So then I have a maximal root with respect to the ordering of the positive roots. I think we discussed this existence uniqueness of the maximum roots at some point. When I have a root, I have a three-dimensional subalgebra. We call it L. This was the root vector H alpha, X alpha plus I X alpha, and X alpha minus I X alpha divided by I. This is a three-dimensional subalgebra in G. That's true for every root. This always defines a subalgebra. We also looked at those at some point. But now I'll do it for the maximum one. So what I'm going to say only works for the maximum one. So this then defines a subgroup L inside G, the one with Lie algebra L, given by the maximum root. And then I'll let K be the normalizer of L. In fact, this L, what can show is SP1. It's three-dimensional, but it's not SO3, it's SO2. So I let K be the normalizer of L, and then G comma K is my quaternion symmetric space. So there's a really nice uniform description of what they all look like, just in terms of simple Lie groups. So classifying simple Lie groups, one gets out of that immediately classification of those symmetric spaces which are quaternion. And that's the construction. Look at the SP1 factor is this natural group, and now you have to show that you have to see how it acts on the orthogonal component of this normalizer. And that's not difficult if you know something about root spaces. I'm starting to include a chapter on these quaternion symmetric spaces, so at some point I'll put that on the web when I'm finished with that. But in the last lecture, we're going to do topology of symmetric spaces. So next week, Monday is the last lecture. We do topology.